Okay, so far we have given lots of models which accept regular language, right? So the questions were like show that this is regular, show that this is regular, construct a DFA for this, construct an NFA for this. Now we move to the phase where we show how to prove that some language is not regular. Okay, so and the primary tool to prove such thing is called pumping lemma for regular languages. So there is another pumping lemma for context free languages, but right now we are only concentrating on pumping lemma for regular language. So this lemma gives you a property about regular language. So it says that if a language is regular, then something happens, and we use this lemma to prove that certain languages are not regular in a contrapositive form, where we show that that something that is supposed to happen that doesn't happen with the given language. So we conclude that the given language is not regular. And you see that proving that something is not regular is it's kind of more challenging in the sense that when you are asked to show that something is regular, all you have to do is to come up with some DFA or some NFA or some automata or maybe a regular expression. Okay, so if you produce that, then it's done. Now if you are asked to prove that something is not regular, you cannot just give some automata or something and say that okay, here is the proof. So you have to prove that no matter what automata you construct, okay, it doesn't matter. I mean, there are infinitely many automata, and all of them, none of them accepts the given language. So in mathematics, it's always the case that this non-existence results are generally harder to prove, or it's generally more interesting to address, because you have no direct way of doing that, right? You cannot just go through the infinitely many possible automata. So that's the technique. We somehow come up with a property that every regular language should follow, and we check whether that property is followed or not. Now see that this is not a if and only if condition. Okay, so it's not that if the language is regular, then this property will follow, but if the language is not regular, then it's not that this property will not follow. So it's a one way sort of method. So if you see that your language is violating this property, then you conclude that your language is not regular. But that kind of suffices for a lot of cases. So without much ado, let's start. So first I would like to just brush up some notations. So you all know that you are using this thing for other branches of mathematics. So what is a proposition? I mean, it's some kind of statement which can be either true or false. Okay, some statement about some variables. Okay, this x1 up to xn are variables. So for example, if you take just say one variable and say this variable has each of the variable has some associated domain with it. So suppose the domains are strings over some alphabet. Okay, so then some example will be say just px, which we used to denote say x is not empty. So this is a statement, and this statement can be just mathematically symbolically written as just px. So px means px is true. Okay, so here is an example of two variable proposition. So qxy means say y is longer or equal in length than x. So this sort of thing, I mean, you have seen this, and it's just a recap. And also we use this notation for conjunction. So logically this means and, right? So this is some statement, this is some statement, and this means that this statement is true and this statement is true, right? So this thing. And this is the implication also. I mean, we use that all the time. So P implies Q means if P is true, then Q must be true. If P is false, then this thing is vacuously true. So I'm not going through predicate calculus, I'm just mentioning this thing. So now a proposition may contain quantifier, right? And quantifier is what? It's either this for all or there exists. Again, there is nothing to explain about for all there exists. The only thing is that if you consider say a proposition containing this quantifier, say this thing, so this is a proposition of two variables, right? We sometimes say it has array T2, so it's a array T2 thing. So now if we do this for all y, this qx qxy, that means for all y this y is greater than equal to x. So now this is not a statement about y, you see, we are not taking any specific value of y. So this is actually a statement about x. In fact, this is saying that this x is empty. If you take this q to be this q, okay, so that means all y's are at least as long as x. So anyway, so that means this is a proposition about just x, not y. And the terminology we use in logic, though these are not required in our case, but this y is a bound variable, so that is why it's just within this thing, and this is a free variable. So the proposition is about the free variable, right? So then we can have a chain of quantifiers. For all x there exists y, for all z there exists w, whatever. Now when we have this sort of thing in front of this thing, and then this y, so this existence of y, okay, so this is dependent on this x. So y may depend on x. So for example, take this again. So for all x there exists y, such that this happens. Now if you are talking about a particular, so for all x you are stating this, but for a x this y is dependent on x, right? So it has to be something more than longer than x. So this y is dependent on x, and again these are just child's play, you know that this holds, but when you have say this 4 or 5 quantifiers, then sometimes the notation gets so complicated that you lose track. But anyway, so I deliberately took this example of involving 4 quantifiers. So again, for all x there exists y, for all z there exists w, such that something happens. And again, so if you have some existential quantifier, then here the value of y that you are considering in this proposition, so that depends on the previous variables. So this y depends on the previous variable, which is x, this w depends on all the previous variables, z, y, x, right? So just read this example and try to see. It's so yeah. So here it actually says that y is minus x, and so y is dependent on x, and then once you have this y, then this w is dependent on z, so it's actually dependent on y, z, and y is dependent on x, so it's dependent on x, y, z. So this sort of thing. So then we have negation. If we have a proposition, then its negation, and we write it like this, right? So this symbol we use. So what is a negation? It's the opposite of the statement. So if this denotes that this is not empty, so then its negation will denote that this x is empty. If this denotes that this is greater than or equal to x, then its negation will denote that it's less than x, and so on, right? And we can, so if we have quantifiers, we can push this negation inside. So see, this is pushed inside, and this quantifier changes. So it happens for both for all and there exists. So this is pushed inside and this changes, right? So again, this is quite intuitive. So without negation, what is it saying? That this is true for all x. So its negation means that it's not true for all x. That means it must be false for some x. So there must exist some x for which this is not true, and this is the statement that there exists some x for which this is not true. Similarly, this is saying that for some x this thing must be true, and its negation is that no such x exists. So that means for all x this should be false. So now again, this you use all the time while proving theorems. So if you have something like some p implies q, so it is equivalent to saying that this negation of q implies negation of p. That means if so, this is saying that if p happens, then q must also happen. So this is saying that q doesn't happen, that means p must not have happened, or if p is true, then q must be true. So this says that if p is not true, then if q is not true, then p cannot be true, right? So it's just a contrapositive form of this thing. And then so this is one way of writing negation of conjunction. So this is saying that both p and q are true, so its negation is that if p is true, then q is not true, right? So this is saying that this whole thing is true if when p is true, then q is also true. So this is saying that p is true, but it implies that q is not true. So it's if you just write it down, this is what it amounts to. In fact, if you break down this implication using conjunction and disjunction, then if you forgot, then this is what it actually is. So this means either a is false or b is true. So this is the disjunction, right? This is the or. Okay, and if you take the negation of this thing, so if you take the negation of this thing, so then this becomes a conjunction, not b. So anyway, these are just basic predicate calculus. So you already know that. I'm just reminding you because I'm going to use that in a complicated examples like this. So we just need to, it's convenient to have all the formulas tabulated. And similarly, if I take the negation of this implication that P must imply that Q is true, so its negation, one form of the negation will be like P is true but Q is not true. Okay. So yeah, these two identities we are going to use. Now look at this example. So here the domain of this n is natural numbers including 0, and all this z, u, v, w, they are strings, and again this I is are natural numbers. So I and n are natural numbers, z, u, v, w are strings, say. So if I have this sort of proposition, so what will be the negation of that? So I can push this negation inside like this and make this for all, and then it's pushed inside. Then I can push it further and this for all becomes there exist by this. Okay, and then we have an implication. So we use this thing. So it's pushed inside and this becomes conjunction, and this is pushed here. So this becomes this conjunction, and it comes here. Then this existential quantifier becomes this for all, and this is pushed here, and then this conjunction. So we use this and write it like this implies not of this. So this becomes this implies not of this, and finally this for all becomes there exists, and this is pushed inside. Okay. So the negation of this will be this. So you see that all the quantifiers are switched, right? So this there exists becomes for all, this for all becomes there exists, this there exists becomes for all, and finally this for all becomes there exists. And also these conjunctions are changed into implication, and implications are changed into conjunctions. So you can blindly do that. Change the interchange the quantifiers and interchange the conjunction and implication, and keep on pushing this inside this negation. Okay. So enough of this recap. So now we come back to our formal language thing. So first we define something called pumping. Okay, so you remember this lemma that we are going to prove and use is called pumping lemma. So what is pumping? So given any language L, see this is any language, it's not just regular or anything. So given any language L, so this is a formal language L and an integer n. So these two things are given, right? This is given and this is also given. So both things are given. Okay. So given to these two things, we say that this z can be pumped. So z is a string over the same alphabet as this. So we are just fixing some alphabet, and we won't explicitly talk about the alphabet. Some alphabet is fixed. So given these two things, this z can be pumped if so this in fact this z is in L. Okay. So z in L and also z has this constraint that z must be at least as long as n, right? So these two are given and we are talking about whether z can be pumped or not. So z is a string in L and length of z is at least n. So this z can be pumped if we can break this z as in three parts. Say UVW, they are this is a prefix of z, this is a substring of z, this is a postfix of this thing. So so z can be broken into this three part such that this middle part is not empty, and if you take this two things together from the beginning, okay, so up to this, so then their length should be at most n. So you see that this n is given, right? This L and n are given. So already we take a z in the L satisfying this constraint, so n is used here, and then we say that this z can be pumped if it can be broken into these three parts such that this two there are three conditions. So first condition is that this middle part is not empty. So this two together from the beginning is of length at most n, and the most important part here is that we can pump this middle part, right? So this z is UVW, right, and z is already in L. So now instead of just UVW, you take UVVW, UVVVW, and all those strings for all I, it's in L. And here also so yeah, so this I, this can also be 0, okay, so this I can be 0, and this can be so this is already 1. For 1 it's already here, so UVW is already in L, but for I equal to 0 and for I equal to say 2, 3, 4 and onwards, so this U V that many times and then W, this should also be in L, okay. So just pause this video, take some time and just digest this definition, what we mean by the statement that Z can be pumped. So again, this Z already follows this constraint that it's a string in L and its length is at least n. And then we say that this can be pumped if it can be broken into these three parts UVW with these constraints that this V is not empty, UV length of UV is at most n, and this V can be pumped for any number of times including 0 and also 1, 2, 3, 4, 5. Okay, so this is what we mean by the statement that Z can be pumped. And if you formally write it down, so see, I mean this so this L and N are given, right? So these are already given. So Z can be pumped. This proposition can be written as that there exists this UVW such that this Z is UVW and this V is not empty, this length of UV is at most n, and for all I this UVIW is in L. So this is formally what it is to mean that Z can be pumped. Okay, but we already have this constraint on Z, that Z is in L and length of Z is at least n. So Z is coming from with that constraint, and then we say that it's pumped if this is true. So one example here I have is so take just this L. Again, we do not know whether this L is regular or not. Let's just pretend that we do not know what it is, and we do not care what it is at this moment. So sorry, there should be a so it's coming from this alphabet, so it's string of a 0 and 1, such that the 0 0 is not a substring of W. That means this W doesn't have two consecutive zeros. Okay. So if you have a 0 either in front of it or at the back of so in both ways there should be a 1, unless this 0 is at the front or at the back. So yeah, so this is what it is. There is no 0 0 as a substring of W, and take all such strings. So that is our language. So take this string. So is this string in L? Yes, it is, because this Z satisfies this property. 0 0 is not a substring. So Z is in L, and suppose our n is suppose our n is what, say n is 4. I should have mentioned it here. So let this thing and let also n equals 4. So given these two things, we ask whether this Z can be pumped. So first we verify that Z is in L and length of Z is at least n, and then this can be pumped if there is a breakup such that this middle part is non-empty and it can be pumped. So we take this breakup. So this we break this into this 1, this 0 1 and 1, right? And then can we pump this thing? So for I equal to 0 we get 1 1, right? For I equal to 1 you get Z. For I equal to say 2 3 or whatever, so you get this 0 1 0 1 0 1 some number of times, and then finally 1, right? So you see that this also doesn't contain this 0 0 as substring, so this is also in L for all I. Okay, here I have taken I equal to 3, but this happens for all I. So this is 0 0 1 1 is for I equal to 0, but this happens for all I. So it satisfies the definition of pumping. So Z can be pumped in this language, okay, with n equal to 4, say. So now what do we mean Z cannot be pumped? So we explicitly again write the formula. So if you take the negation of this, what do you get? So negation of this whole thing, that means this quantifier is changed into for all, and the negation will be pushed inside. So then this is a very big conjunction. So we can break it down into a conjunction of, say, here to here, say, and this part. Okay, so this part and then this whole part. So as we saw, the negation of conjunction is again you push the negation inside at this place, and you replace this by implication, right? So this implies that not of this thing, and not of this thing means what? Again, this will become there exists, and the not will come here, so that means negation of this is this. Okay, so instead of just blindly executing this equations or formula for generating negation, intuitively also you can see that this is the case, right? So this is saying that okay, given ln and with this constraint, so these constraints are not part of this, so these constraints are already there. So it says that for all breakup something happens. Okay, that something is here. So that means that its negation should be like that there exists some breakup for which that something doesn't happen. So that means sorry, this says that there exists a breakup for which something happens. So the negation is that for all breakup that something doesn't happen, and that something is saying that okay, with this property, so this property, this V part can be pumped, right? So, and this is saying that with this property, this V cannot be pumped, and cannot be pumped means at least there exists some value of I such that this pumped up string does not belong to L, right? So again, you just there is nothing to explain anymore from my side. So you just pause this video, try to just go through this, and not just read the symbols, but intuitively you kind of convince yourself that this is the negation of this, right? Because this should come naturally. The Z can be pumped means that there exists some breakup for which you can pump this middle part. So this says that then for all breakup you cannot pump this middle part, and then these are also thrown in, so these constraints. So the main thing is that this quantifier and this pumping part. Okay. So you just take your time and try to digest that thing. Okay. So first of all, here we have two quantifiers. This existential quantifier is down below here, and as we mentioned here, this variable may depend on the previous variable. So here the previous variables are here, UVW, right? So that means when you are kind of proving that some Z cannot be pumped, so for all UVW you have to come up with some I such that this UVIW is does not belong to L, and this I can depend on what particular breakup you are considering, but you have to consider all breakups, right? So this is the important part. You have to, when you are trying to prove that something cannot be pumped, okay, so when you are trying to prove that something can be pumped, then any one breakup is okay. So I forgot to emphasize on this part. So sometimes students get confused, like okay, this pumping is fine for this breakup, but if I take some different breakup, say U is 1, V is 0, and then this W is 0, 0, so then I cannot pump, right? So 1 and if I pump this thing, it becomes 0 0, this becomes 1 1, and this does not belong to L. So can we pump Z or can we not pump Z? So you should not ask these stupid questions, because there's a existential quantifier here, right? So it is saying that if there exists any breakup, so any breakup which satisfies this part guarantees that this Z can be pumped. Okay. So similarly, when we negate this thing, so you have to show that for all breakup, here you need to consider all breakup, such that the string cannot be pumped. Okay. So yeah. Now again we take some example. So this is just a language. Again, we do not care at this moment whether it's regular or not. So 0 to the I, 1 to the I for all I including 0, and again say this n is 4. Okay. So we take this string in L. Obviously this is in L, and mod of Z, length of Z is at least 4. So those two constraints are, so these two constraints are already satisfied. Now we ask, can Z be pumped? So suppose you are trying to argue that Z cannot be pumped, and here is your argument that okay, we take this breakup, this 0 0 1 1, so 0 0 1 1, so UVW, and then if we pump, so pump doesn't mean this I has to increase, so this can be 0 also, as I mentioned. So in fact, other than I equal to 1, you see that for any other UVIW, this thing will not be in L, right? So there will be a mismatch in the number of zeros and ones. So this is not in L, so Z cannot be pumped. Now the question is this argument correct? Okay. Again, pause the video and try to answer it yourself. Is this argument correct? Okay. Okay, so this argument is not correct because, as I mentioned explicitly, in order to prove that this Z cannot be pumped, you have to consider all breakups. Okay, and for all possible breakups, you have to show that this UVIW cannot be pumped. So you cannot just take one breakup and show that it cannot be pumped and say that that is why Z cannot be pumped. So that worked for the case where you are trying to show that Z can be pumped. Okay, because there we had this existential quantifier. So any one breakup is fine, but when you are trying to argue that Z cannot be pumped, you have to prove that for all possible breakups Z cannot be pumped. Okay. Now consider another argument. So since this argument for showing that Z cannot be pumped is false, so is it then the case that Z can be pumped? So we take again this breakup 0 0 1 and 1, and then we argue that since this string, so what is this UV0W? It's just UW, that is 0 1, right? U is 0 and V is W is 1, so this is just 0 1. So this is in L. If you see the definition of L, this I you take 1, so 0 1 here. So okay, we take one breakup and we show that this thing is in L, so then maybe Z can be pumped. because for showing that something can be pumped, only one breakup was okay, right? So this for all is for showing Z cannot be pumped, and we in the previous slide said that to show that something can be pumped, you just need existential thing here, so any one breakup will do. So is this argument correct? Again, take some time and try to answer, if you have understood up to this point. So this again is not correct, because you see this was the thing. So there was a existential quantifier here, but here we have a for all thing. So for all I, this should be in L, right? So you have to be very, very careful while proving something is while using this pumping lemma. So we haven't stated pumping lemma yet, but even to understand what pumping means, you have to be careful. So you cannot just take one particular value of I and since it's in L, say that this is. So here some particular value of I is fine. So here you see that you have to take all breakup, and for a chosen breakup you take some particular I which is dependent on UVW and show that this is not in L. So here one particular choice of I is okay, but you have to consider all possible breakups. Here it's the other way around, right? So here any one breakup is fine as long as you can show that for all value of I this is in L. Okay, so this there exists and for all, so they are changed. So both are false. So then what is it? Is this, can we pump this Z or not? So in fact we cannot pump, but to prove that we cannot pump, the correct argument should be this. Okay, so so what did we say? That you have to consider all possible breakups, and for each breakup you have to just provide one I such that this thing doesn't belong to L. So now if you take Z of this form and N is 4, so this breakup should satisfy what condition? First of all, this should be a breakup of Z, and it also should satisfy these two constraints, right? So this middle part is not empty, and this UV must be less than equal to N. Okay. So just I'm mentioning that U or W, they can be empty. So this U and this W, they can be empty, but this V part cannot be empty. So then it doesn't make any sense to say that this is being pumped. So this is this V is not empty. So if these are our parameters and this is our Z, how to correctly argue that this cannot be pumped? So you consider all possible breakups, and all possible breakups can be classified into these three cases, where this V part, so this is U, this is V, this is W. So here this V part consists entirely of zeros. Okay, so you have some zeros, then this V is again some zero, and then this W is the remaining zero and this remaining two ones, right? So this L should be at least 1, right? Because this V is not empty. So either V is 0 or V is 0, 0. So correspondingly, if V is 0, then this is 0. If this is 0, 0, then this is empty. And then okay, this can be empty and this can be 0 also. But whatever 1 or 2 zeros are consumed here, either here you have many zeros or 1 0, and so this part will be W. So this is one case. Another case is when this V is entirely consists of this one part. So V is either here, this one, this, or V can be just this two ones also. Then this W will be empty string. So yeah, these two cases are V is consists entirely of zeros, V consists entirely of ones, and then this says that it consists both zeros and ones. So V can be anything which contains this boundary. Okay. So it can be either 0 1, it can be 0 0 1, or 0 1 1. Okay. So these three cases are these three possibilities are covered in case 2. And for all these cases, you can pick some I such that this UVIW is not in L. So here, if I pick V0, that means you are removing 0, right? So you are removing L many zeros. So the number of ones and number of zeros mismatch. So here again, you are removing L many ones because you are removing V if you are taking I to be 0. So then this number of ones becomes less. And here you can take I equal to 2. So then this kind of becomes some 0. So you have some 0 for U, and then this V looks like some zeros and ones. So then you also have, if you pump this twice, then you also have some 0 1s and then something. So you have alternation of 0 1 0 1, but that is not allowed here, right? So you have all the zeros here, I many zeros, and then I many ones. So you cannot have a 0 1 and then a 0 1, something like that. So this is also not in L. So you have to consider all possible breakups, and you have to provide a corresponding I such that this is not in L. So if you can do that, then you can correctly claim that this Z cannot be pumped, and here we have actually proved that this Z cannot be pumped. So Z cannot be pumped. Okay. So sometimes this number of cases are greatly simplified for other choices of Z here. For example, if I choose Z to be, say, 0 to the 4, 1 to the 4, right? So then you see, by this constraint, so UV must be less than this UV together can be of length at most n. So that means when we are breaking this up, okay, so this U then comes V, but this UV together should stay within this limit, right, within this zeros, right? So W will consist entirely of ones or maybe some zeros. So W is either this or this or this, but UV consists of only, say, 0 or 0 0 or 0 0 0 or 0 0 0 0. So this UV part is this. So that means V itself consists of only zeros. Okay. So then the only type of breakup is where V consists entirely of zeros. Obviously, U will be entirely consists of 0, and the rest are in W. And here also it's quite easy to prove that it cannot be pumped, because if you just remove this or repeat this twice, thrice, or any number of times other than 1, so then the number of zeros and ones will mismatch, right? If you take this V 0, then this is reduced, and if you take this I many times, in fact you have, so for a general expression will be what? So if you take U V I w. So this will be 0 to the 4 plus this length of v times I minus 1, and then 1 to the 4, right? So length of v. So you see that there should be a mismatch in number of zeros if this I is not equal to 1. So z cannot be pumped, but here the number of cases is greatly simplified because of the choice of z.